We're going to talk about the 6 trigonometric ratios. Mainly, what we're going to find out as part of trigonometry, the course is going to basically revolve around these two things. If we can remember those two things, then we should be able to remember, or not necessarily remember, but understand the relationship to generate these other four. Um, and then all of trigonometry kind of revolves around those 6 trigonometric ratios. How we implement them, how we use them, the other relationships that generate from them. Um, from geometry, basic geometry, back to freshman sophomore year, if we defined a angle, okay, so maybe we're gonna look at this angle here, theta, okay, and it would change per angle we look at. We're only going to look at the acute angles of a right triangle. So this is only true. These things are only true here for the acute angles of a right triangle. Okay, so we're going to look at here at theta, or this angle up here, which would be 90 minus theta. Um, if we remember things about the acute angles of a right triangle. Um, so looking at this, so we could call that the complement up here to theta. Um, but if we identify theta and then start labeling these sides of the triangle in reference to theta. So if we go across the triangle, we get to this side, which is opposite theta. Opposite theta. Okay. Um, then the adjacent side is the side that is helping create the angle theta. Okay, there's two sides that are going to create theta. One is always going to be the hypotenuse, and one is always going to be the adjacent side. Okay, they're both adjacent, but the word hypotenuse supersedes being adjacent. So we'll call that one the hypotenuse, and this one the adjacent. Okay, so if we were to flip things around a little bit, so let's say that I'm looking at, let's say we're looking at this angle up here. Let's call it, oh, it's really big. Let's say we're looking at this angle beta up here. Okay, now this would be opposite. This would be adjacent. That would still be the hypotenuse. Okay, so it's all going to be per the angle that we are referencing. Okay, we had in geometry, we had a mnemonic device that helped us remember these names. So basically what happens here is that we've just got ratios. Okay, if I compare this opposite side to the hypotenuse, the opposite side divided by the hypotenuse. So I compare them through division, okay? We could do that for every right triangle. We can take an angle and divide an opposite by hypotenuse. But there's going to be a lot of opposites divided by, because this could be an opposite and that could be a hypotenuse. So what we're going to do is we're going to reference that off of an angle. So we have to identify the theta that we were dealing with. Okay, so I'm referencing this angle. And then they say, okay, well, instead of just saying opposite of hypotenuse every single time, we'll just say sine of theta. And if you could do a little bit of, people always ask, well, why is it sine? And that's an abbreviation for SINE. And I'm not going to get into it in this video, but there's a logical reason why we use the word sine. Cosine, tangent, and at some point during the course, I'll show you the pictures and work through the nomenclature of this section, essentially. But that's how we identify the sine function. It's opposite divided by hypotenuse. Okay. So if we take the first letter of sine, first letter of opposite, first letter of hypotenuse, we get the acronym SOH. We can then do the same thing with cosine, and cosine is the adjacent divided by hypotenuse, the adjacent side divided by hypotenuse. So that would be taking the first letters off of those, C-A-H. So we refer to this as so, and this is ka, and then the tangent, you maybe reference or remember that tangent is opposite or adjacent. So we get this TOA. Okay, so that's a mnemonic device that helps us remember these three relationships. And basically what it says is, or what this means is, no matter what, as long as I've got a triangle, let's say I have a triangle that has a 30-degree angle in it. I'm going to try to demonstrate this with a GeoGebra. You've seen this GeoGebra before. I made this several years ago um, to explain the concept when we were in geometry. Because basically what we're going to do, we're going to use our calculator a lot to get these values for us. And there's going to be some that we memorize. But let's say I have a triangle that has a 30-degree angle. Okay, so we've got that triangle there. That triangle there, 30-degree angle, is going to be different than that triangle, which is going to be different than that triangle, which is going to be different than that triangle. Okay, but they all have a 30-degree angle in them. Okay, and if you remember anything from geometry, if we had, if we had a triangle that had a 30-degree angle and a right angle, okay, and then another triangle that had a 30-degree angle and a right angle, that those two triangles had what we call angle-angle similarity. Okay, so what angle-angle similarity states let's say that I've got, just trace this triangle out. Let's call that triangle A prime, C prime, B prime. And then let's just make, let's see if we can do this. So then we've got this triangle that I traced out, the bigger one, call it A prime, B prime, C prime. And we've got this shaded in triangle, ABC. Okay. Because they both have this angle right there to be congruent, and they both have angle A, we say these two triangles are similar by AA. Angle-angle similarity. Which that leads us to what we learned in geometry said, if two triangles are similar, that means that their segments, A prime, B prime, okay, so segment A prime to B prime, which would be the hypotenuse here, is the same as, or is comparable to AB, which is then comparable to B prime C prime, which will compare to BC, which we're going to compare to A prime C prime over AC. And I keep saying comparable, but we use the word in geometry proportional, meaning that they have the same ratio when we compare them. Okay, so when we look at these now, I didn't write them the same way in the GeoGebra. But if I'm looking at this 30-degree angle and I say opposite over hypotenuse, so opposite, which would be C prime, B prime, over hypotenuse, which would be A prime, B prime, or AB. Okay, so I'm looking at this segment compared to that segment, or this segment compared to that one. And what we're going to find out here is if I look at, so BC compared to BA, so I'm going to look at that right there. And in this little triangle here, they're showing us that turns out to be 7.15, so this distance here is 7.15, and the hypotenuse right here is 14.3. Okay? But the moment that we make that grow, see if we can get it back to roughly that triangle. Now we have that distance B prime to C prime as being 14.15 and 28.31. Okay? Much different than what we had right there. These two values are different. But if you look at their quotient, okay, So let me write that one down. So A is BC compared to okay. So what I have here, if you remember back to um, geometry. So I compared ultimately like a hypotenuse to a hypotenuse. This is opposite side compared to opposite side. This is um, adjacent side compared to adjacent side. Let's kind of tackle just looking at these two real quick. What we talked about in um, um, geometry was if I have a proportion like a prime b prime over ab equal to b prime c prime over bc. I'm going to do two things here so that I can realize this proportion. We can do two things. We take the reciprocal of the left-hand side, so that's going to turn into AB over A prime B prime. And we can take the reciprocal of the right-hand side, which would be BC over B prime C prime. Just so that we can see this maybe happening a little bit easier, let's actually write this here on this side. And actually, it would have been easier if we just done this. So everything right there is fine. But let's just do this. Let's just rewrite this one on this right-hand side. So basically using the symmetric property of equality to rewrite it this way. So that's true. Okay, so that's just taking this proportion and flipping its order. What we talked about in geometry is that we can have a proportion that is true, so that just means this fraction is equal to this fraction. If we interchange those two things right there, so it becomes b prime c prime over a prime b prime, that is the same thing as bc over ab. And now we're seeing bc over ab as being, from this 30 degrees, it's the opposite side over the hypotenuse. Okay, so we're seeing that in this shaded triangle that distance is 14.15 over 28.31, and it reduces to 0.5. Now, if we were to go back to that triangle there, you see now the 14.15 is actually a 7.15, and the 28.31 is a 14.3, but they still both reduce to 0.5. And basically what that's telling us, and we can do this with all types of, I can change this as much as I want to. You see the numerator and denominator is consistently changing. Okay, but because of angle similarity, the opposite side divided by hypotenuse of a 30-degree angle, okay, is always this side, whatever its length is, divided by that side, will always be 0.5. And for similar reasons, then, when we get to like a 30 or 40-degree angle, the relationship will always be the opposite side divided by the hypotenuse will always be 0.64. Okay, we can go back and make this a little bit simpler, at least for a 30-degree angle. We know that with a 30-degree angle, from the last video that we talked about, in a 30, 60, 90 triangle, this is n, and this is 2n, and obviously this is n radical 3. So then when we talk about opposite divided by hypotenuse here, this would be n over 2n, and you're going to see that reduces to 1 over 2, or 0.5. And that's what these two always compare to. If I double that top one, I get the bottom one, no matter what. If we were to show, so similar relationships, that's the sine, okay, so sine of any 30-degree angle is going to be 0.5. Now if I go sine of 40, it's always going to be 0.64, okay. Now eventually we get into something called Taylor series when we get into calculus, and I think there's something called Maclaurin series that actually allow us. It's essentially a function that's going to allow us to know this 0.64 and calculate this 0.64. Okay, but that's what's happening every time that I take. You see here now as I change the side lengths. So now the hypotenuse is 36.16. This inside is 23.25. The way they divide will always be 0.64 in this case because of that 40-degree angle. Okay. So likewise, if I do this one, so CA divided by BA, so that's adjacent divided by hypotenuse. So adjacent divided by hypotenuse, if I'm looking at a 30, 60, 90 triangle, it's n radical 3 divided by 2n, and that's radical 3 over 2. And this here, I think radical 3 is about 1.7 something divided by 2, approximately 0.87 is what that turns out to be. So now no matter what I have, no matter how big my triangle is, as long as it has a 30-degree angle in it, the adjacent side divided by hypotenuse is always 0.87. Okay? And that all stems back to that idea about when we have two triangles that are similar. Kind of write this again. If I have, let's actually go back to this here. It might be easier to write. So if I've got let's say that angle is my right angle. Let's say we have theta here, and let's say beta down here. And then I have another triangle where that's a right angle, still theta, still beta. Okay, so just as long as theta is the same as theta and beta is the same as beta, if we look at, let's just call this A, B, C, and then A prime, B prime, C prime, if triangle ABC is similar to triangle A prime, B prime, C prime. Okay, so that's geometry. Okay, back 9th, 10th grade. And from that we were able to get the idea that if two shapes are similar, then corresponding parts, corresponding sides, are proportional. So AB will compare to A prime, B prime, BC to B prime, C prime, and AC to A prime, C prime. Okay. Now, if I want to look at just comparing those two, okay, what we can do is, like I said, I'm going to rewrite this as BC over B prime C prime equals AB over A prime B prime, and that's just taking this first one and just flipping these two. Okay, you can do that with symmetric property. And now if I interchange the means, I get BC over AB, and I get, so interchange G, so B prime C prime over A prime B prime. So let's look up here what those are. So BC, so if I'm looking at BC here and comparing that to AB, okay? So let's look at beta. If I'm looking at the angle beta, I've just said that the opposite, let's do it this way, theta. Let's look at theta. If I'm looking at theta, we just said the opposite, which is BC, compared to the adjacent, which is AB, in this triangle, which is a smaller triangle than this one. that the ratio of BC to AB is the same as the ratio of B prime C prime compared to A prime B prime. So those two, the comparison of that set of segments to that set of segments, even though the segment lengths here in the triangle on the left are smaller than the segments of the triangle on the right, their ratio is the same. And in this situation, because we're looking at opposite over adjacent, that's the tangent relationship. Okay. If we were to look at, let's say, those two, okay, so let's rewrite that as, I'm just going to interchange these means, right? I have to leave it the way it is, interchange those means, so I got BC over AC, when I interchange those two things, and then I'll have B prime C prime over A prime C prime. So BC compared to AC, so BC, looking at theta again, BC would be opposite, AC would be hypotenuse. So we're saying that the quotient of whatever those two distances are is going to be the same as the quotient of these two distances, B prime, C prime to A prime, C prime. Okay, so right there, that is the opposite divided by the hypotenuse. So that relationship right there is what we're calling sine. So this was tangent. And now let's look at the first one and the last one. If I've got AB over A prime B prime equals AC over A prime C prime. Now let's interchange those means again. So I have AB over AC equals A prime B prime over A prime C prime. So if I look at AB compared to AC, AB, which is the adjacent side, AC is the hypotenuse. So right now I'm saying, I'm talking about the cosine. This adjacent side divided by, so this adjacent side divided by this hypotenuse is the same then as A prime B prime, which is this adjacent side, divided by that hypotenuse. And because I never used any specific values for theta or AB or BC, we're now seeing that no matter what theta is, the sine, let's say the sine of 30, and no matter how big that triangle is, it's always going to be 1/2. The cosine of 30 is always going to be what ends up being radical 3 over 2 or 0.87 all the time, no matter how big the triangle side lengths are. It's because of this idea of similarity. So that's a key idea that you need to wrap your head around. And if you understand that, that's going to make the rest of this course so much easier. Basically, we know that every single time that we see a specific angle in a triangle, we don't really care how big those side lengths are. We know they're going to reduce to 0.5. And what that allows us to do then is to say, eventually, okay, if I've got this 30-degree angle, and I know that, let's say this, I'll just make an easy one, this side here is 5, then we know, because it says sine of 30, should always reduce to 0.5, should always be 1 over 2. I've got the 30, I've got the opposite side being 5 here. What does the hypotenuse have to be in order to get a 1 to 2 relationship? Well, that hypotenuse has to be 10. And what that allows us to do is eventually say, okay, well, let's write it this way, that sine of 30 is equal to blank, or sorry, not blank, 5 over blank, cross multiply, x sine of 30 equals 5. Now we know sine of 30 has to equal 1/2 always. So we get 1/2 x equals 5. How do I solve for x? Multiply by 2. X is 10, and now I know the length of my hypotenuse. So that's kind of the benefit of knowing these ratios. Just a general practice that they're going to ask us to do initially is just to take a triangle. They're going to give you the parts, all 3 parts, and they're going to ask you to write the 6 trig ratios. Okay. Now I didn't mention these, but come up here and let's talk about these bottom ones here. If I look at these, so opposite over hypotenuse is sine. If I look at this is hypotenuse over opposite. So these are reciprocals. Okay, so sine and cosecant are reciprocals. Cosine and secant, likewise, are reciprocals. Okay, if you look at these two, let's see here. Control Z. All right, if you look at those two, okay, there's a word that starts with S and there's a word that starts with C, sine and cosine, okay, respectively. If you look at these bottom two, the same thing happens. One of them has a C, one of them has an S, okay, to start out with. When we refer to reciprocals, the way I remember which one is which, the C and the S's do not go together, okay? So, like, for instance, sine will not go with secant because they both start with an S. Okay, cosine will not go with cosecant because they don't both start with or they both start with a C. They need to be opposite letters essentially in this case. People always get them confused. Okay, so that's the way I remember. I'm not saying that's the only way. Just figure out some device that can allow you to always attach those two together as reciprocals. Okay, these two as reciprocals, those two as reciprocals. Okay, there will be eventually, okay, a relationship maybe between cosine and cosecant. Okay, there might be a relationship between sine and secant. Okay, cosecant, secant. This is cotangent. Okay, and if you guys remember tangent, what tangent meant, so I have a circle, and I have a line that touches that circle one time. That line was said to be tangent to the circle. There's relationship there of why we call this tangent. Okay, if you remember secant refers to a line that passes through a circle or a curve two times. There's that geometric relationship is a reason why we call this a secant, this relationship is secant. And like I said, I'll show that to you eventually. We've got some drawings that make that obvious. All right, so down here is what they're going to ask you to do is say, okay, well, can you find sine of theta, cosine of theta, tangent of theta, okay? And then I always write the reciprocals on the side. So sine has to go with cosecant, S and C. And this was C, so it's got to go with secant. And then cotangent is obvious. All right, so if I get the sine is opposite over hypotenuse, so 2/3. So what's nice about that is once I have that to be 2/3, I automatically know its reciprocal is 3/2. Cosine is adjacent. So this is the adjacent side. This was the opposite side. This is the hypotenuse. So cosine is adjacent over hypotenuse. So radical 5/3. The secant then is 3 over radical 5, which we will always rationalize that. So 3 radical 5 over 5 is what we're looking for there. And the tangent is going to be opposite over adjacent, so 2 over radical 5, which is going to be 2 radical 5 over 5. And then the cotangent would be the reciprocal of that, which I'm going to take the reciprocal of that one because it automatically rationalizes it. And that's the 6 trigonometric ratios of the angle theta. Now, what I want you to recognize here, real quick, is that if you know sine and cosine, you should automatically know those two, simply just because they're reciprocals. Okay. Now, I'm going to take this number right here, 2/3, and I'm going to divide it by radical 5/3. And when we divide a fraction by a fraction, the way we do that is we take the reciprocal of the bottom fraction and multiply it by the top fraction. So what that ends up, that cancels and that cancels. It leaves me 2 over radical 5. Well, if I look at 2 over radical 5, that's that number right there, which is the tangent. So what did I do here? I took, that was the sine, and that was the cosine. So the sine of theta divided by the cosine of theta ended up giving me the same thing that the tangent of theta gave me. So that's nice because now If I know these two things, I automatically know these two. And if I divide them, sine divided by cosine, it automatically gives me that one. And if I take that one's reciprocal, it gives me that one. So my hope is that we realize from that demonstration right there, as long as you know those two, you know all 6 of these things. All right, this is perhaps maybe one of the most utilized type of question that we see throughout the course, and it's going to evolve into more and more difficult concepts depending on what they provide us and what we need to find. It says if cosine of theta equals 3/4. So what they're telling us right now is that we have some triangle, and I like to draw my triangles in the coordinate plane here. If I have some theta, okay, and it has to be one of my acute angles on my right triangle. I'll never use my 90-degree angle as theta, okay, because it doesn't make sense to find out what would be opposite and adjacent to a 90-degree angle. So this is opposite theta. This is adjacent. And this is the hypotenuse. So when it says the cosine, which is, remember, adjacent over hypotenuse, we're looking at this being 3 and this being 4. And if they want us to figure out what the other 5 trigonometric ratios are, we need to figure out what this opposite side is. Okay? I see it, buddy. Jelly bean. So the way that we're going to find this opposite side is the Pythagorean theorem. So we'll say 3 squared plus the opposite side squared should equal 4 squared. So we're looking at 9 plus opposite squared equals 16. So opposite squared is equal to 7. So the opposite side is going to be root 7. Okay? So root 7. So now if I want to find the other trig ratios, so if those are if that's the value for the opposite side. Okay, so when we go sine of theta, it's going to be opposite of hypotenuse, so root 7 over 4. Cosine we already know. I'll write cosine here. Cosine of theta was 3/4. Tangent of theta, do it one of two ways. You can either divide these two by one another, so sine over cosine, so you can get radical 7 over 3, or you can come over here and do opposite over adjacent, and you still get radical 7 over 3. And then, so now the sine's reciprocal is cosecant, so 4 over root 7, which turns into 4 root 7 over 7. Secant of theta will equal 4/3, and then the tangent, its reciprocal gives me cotangent, which would be 3 over root 7, which turns into 3 radical 7 over 7. And what you could do is you could, let's see if I can manipulate this for us to prove or validate this.
Mama, Dada.
Alright, so what I've done here is just to show what we've done here is actually like legitimate, makes sense, is going a little bit further than what we've been shown so far, but we do know from geometry about inverses. Okay, so if cosine of theta equals 3/4, we can actually take the inverse cosine function, which on your TIA 384 is like the second, and then hit cosine button and puts that cosine with a -1 above it, and we'll get to that all this course at some point. If I do that, it gives me a 41.41 degree angle, okay, which would this be angle, that angle right there. And basically all I want to demonstrate here is if I make the adjacent side 3 units long, okay, so it's going to put a point right there, 3 units long. And now I'm going to make a line that's perpendicular through 3, so now I've got a right triangle here. So I want to look at this. Actually, I need to get an intersection point here real quick. Intersect that with that. So looking at this triangle here, okay, we can be guaranteed now, if I hide this stuff, just to make it easier to look at, looking down here at these values down here, and let me put the segments so we can identify them easier. Show labels, there we go. Alright, so we said cosine was 3/4, okay, which obviously you're seeing here. E, can I put the numbers with these? Let me see if I can. Properties, name and value. Alright, so if I go cosine, it's adjacent divided by hypotenuse, so that's 3/4. If we do sine, we said sine was radical 7 over 4, okay, which would be this distance of b divided by d, which is 0.66. But if I type in square root of 7 divided by 4, you see that's the same 0.66. So hopefully that, so I've got the cosine, I've got the sine, then obviously the tangent, if those two things are true, then the tangent's going to be true, the secant, the cosecant, the cotangent are going to be true. So this theta, if it were 41.41 degrees, these 6 trig ratios would materialize. Here's a table. I'm not going to make you memorize this table. When I was in school, they said absolutely memorize this table. I think that's dumb, for the mere fact that if I've got a 30-degree angle, so we can change that to radians if we needed to using pi over 180, okay, as the conversion factor. And if I wanted these 3 things right here, well, those are from a 30-degree angle. If it's a 30-degree angle, it's a right triangle, so it's a 30, 60, 90 triangle. So these things occur because of the 30, 60, 90 triangles. So if I remember n2 and n radical 3, I should be able to come up with these 3 ratios by comparing the opposite side by the hypotenuse, the adjacent by the hypotenuse, and the opposite by the adjacent. And then if I go down to 60, so 60 would be the complement of 30. So 60 is the complement of 30. That means that the sine of 60 has to be the cosine of 30, and vice versa. The sine of 30 has to be the cosine of 60. So this row here, if you look at those two, they are these two flipped. There is an inverse relationship there too, that we'll talk about down the road. And then the tangent, that is 1 over radical 3. Well, if I flip that, I get radical 3. Okay. That relationship, just again showing you real quick. If we have this angle here of alpha, and this is opposite, this is adjacent, this is the hypotenuse, and let's just call this beta, the sine of theta would be for this, let's actually call this distance here like W. Let's call this one R, and let's just call this M. For theta, obviously sine of theta would be opposite over hypotenuse, so W over M. Okay. Well, how do I look at beta? How do I look at beta and get the same W over M? Well, beta, if I get W over M, for beta, W would be the adjacent side, and M would be the hypotenuse. Well, adjacent hypotenuse is cosine. That's how we get W over M. So if those two things are the same, then those two things are the same. So sine of theta is equal to the same thing as cosine of beta. Now what we find out, or what we usually like to do, is instead of calling this beta, we say that's theta and this is 90 minus theta, because the acute angles of a right triangle are complementary. So we say that the sine of theta is exactly the same thing as cosine of 90 minus theta. That is a key relationship that we must commit to memory. Okay. We'll stop there for today. I guess I was talking about this list and remembering this list. My hopes are that we know that one because of 30, 60, 90 triangles. We know that one because of 30, 60, 90 triangles. This one we know because of 45, 45, 90 triangles. This we'll get to, that we'll get to. And if we know those two, we automatically know that one. So, but again, I don't want you to memorize this information. Okay, just know it from your special right triangles.